Now that we know how to take a limit, this allows us to examine the idea of the derivative of a vector-valued function. Vector-valued functions can be used to describe motion in space, which means that their derivatives are going to capture the instantaneous changes in that motion. And we'll see, just like we did for limits, that we can differentiate component-wise. Let's take a look at why component-wise differentiation makes sense. So if we have a vector-valued function r of t in component form, remember that we can rewrite it as in terms of the components times the vector I, the vector j, and the vector k. We can use the standard definition of the derivative from Calc 1 that r prime of t is the limit as h approaches 0 of r of t plus h minus r of t. If we then use our component or our addition formulation for our function, this becomes the limit as h approaches 0 of x of t plus h times I plus y of t plus h times j plus z of t plus h times k minus x of t times I minus y of t times j minus z of t times k, all divided by h. And then we can use the commutative property of addition to rewrite this as x of t plus h times I minus x of t times I all over h plus y of t plus h times j minus y of t times j all over h plus z of t plus h, hopefully you can see where this is going, times k minus z of t times k all over h. And then we can factor out our vectors. So this gives us the limit as h approaches 0 of x of t plus h minus x of t all over h times the vector I plus y of t plus h minus y of t over h times the vector j plus c of t plus h minus c of t over h times the vector k, which means that we get x prime of t times I plus y prime of t times j plus z prime of t times k, which can be rewritten in component form as x prime of t, y prime of t, z prime of t. And we get, that we can write our vector we can differentiate our vector by differentiating each of its components. So, short version of all of that is that if you have a vector valued function, then you can take its derivative by just taking the derivative of each of the three components, assuming it's three-dimensional, that define the vector value function. Geometrically, what this means is that a derivative is going to tell us something about the direction of motion along a path. The tangent here is going to be a tangent vector, and it is going to be the direction vector for that motion. The magnitude of the derivative, the magnitude of that tangent vector, is going to tell us something about how fast or something might be moving along a curve at a specific point. We'll see that we have analogs for most of the derivative rules that are familiar to us for real valued functions for our vector valued functions. So what we're going to do here is assume that u and v are two different differentiable vector valued functions. I suppose they could be the same, but u and v are vector valued functions. F is going to be a differentiable scalar valued function. In other words, f takes an input like t and it spits out just a number rather than a vector. And c is going to be a constant vector. So with those ideas in mind, let's look at some of these rules. First, the derivative of a constant vector is going to be 0. each of its components will be 0, so its entire derivative will be the 0 vector. If we take the derivative of one vector valued function plus another, that's going to be equal to the derivative of the first vector valued function plus the derivative of the second vector valued function. If we take the derivative of our scalar valued function times times one of our vector valued functions, f of t times u of t, we get f prime of t times the vector u of t plus f of t times the vector u prime of t. If we compose a vector valued function with a scalar valued function, so we get something of the form u of f of t, then we're going to get u prime of f of t times f prime of t. If we take the derivative of the dot product of two vector valued functions, we get u prime of t times v of t plus u of t times v of t, or times in this case means the dot product. And lastly, if we take the derivative of the cross product of two vector valued functions, we're going to do u prime of t cross v of t plus u of t cross v prime of t. So those last two in particular look like versions of the familiar product rule, but since in vectors we don't have vector multiplication, we have dot products and cross products, we replace multiplication with the corresponding dot or cross product. Let's start with a straightforward example. We're going to take the derivative of the vector valued function t squared sine t e to the t. So the component-wise definition tells us that that derivative is going to be the derivative of t squared, the derivative of sine, and the derivative of e to the t. In this next example, we're going to find a tangent vector. So the tangent vector at t equals 0, this is just going to be the derivative evaluated at 0. So r prime of t is the vector negative sine of t, cosine of t, 1. So r prime of 0 then is the negative sine of 0, which is 0, the cosine of 0, which is 1, and 1. All right, this next example asks us again for a tangent vector, but now it's asking for something called the unit tangent vector. The unit tangent vector. This is going to be an important concept. The unit tangent vector is denoted with the letter t, and the unit tangent vector is going to be r prime of t divided by its magnitude. And we can find the unit tangent vector at a point, or we can find a general formula for this. This asks us to do it for t greater than or equal to 0, so we're looking for a formula for that unit tangent vector. So we're going to take r prime of t, which is going to be e to the t, 3e to the t, and negative 2e to the negative 2t. And then we're going to divide that by its own magnitude. Well, the magnitude of that is e to the t squared, which is e to the 2t, or it's the square root of e to the t squared, which is e to the 2t, plus 3e to the t squared, so that's 9e to the 2t. And then we're going to get plus, when we square the last term, we get 4e to the negative 4t. And we can tidy that up a little bit, so we get e to the t, 3e to the t, this should have had a comma here before, negative 2e to the negative 2t, all divided by, we have 10e to the 2t plus 4e to the negative 4t. All right, in this one, we're going to need to apply one or more of our derivative rules. We're asked to find, given the vectors u of 0 and u prime of 0, and the vector v of 0 and v prime of 0, we're asked to find the derivative of the cross product of u and v. Now, one really important thing to note here is that cross products are not commutative, so we have to get this in the right order. So our rule tells us that the derivative of the cross product is going to be the derivative of the first crossed with the second plus the first vector function crossed, or the first vector crossed with the derivative of the second. In particular, if we look at the derivative with respect to t of u of t crossed with v of t at 0, we're going to get u prime of 0 crossed with v of 0 plus u of 0 crossed with v prime of 0. All right, well, we know what those vectors look like. So u prime of 0 is 1, negative 1, 2. V of 0, so we're crossing that with 0, 2, 1. And then u of 0 is, whoops, that's what I just wrote down as u prime of 0. Let me fix that. This should have been 2, 0, negative 1, cross with 0, 2, 1. And then I'm going to add to that 1, negative 1, 2, crossed with v prime, which is 1, negative 1, 3. All right, so let's do the work for these cross products. We'll do this one first. That is going to be 2, 0, negative 1, 0, 2, 1. So the reason you have to be careful about the order of these is notice that in the determinants, you'll end up with negative values if you get these, if you reverse the rows in this. So we get 0 minus negative 2 times I minus 2 minus 0 times j plus 4 minus 0 times k for our first one. So that is going to be the vector 2, negative 2, 4. And then we'll do our second one. So we have 1, negative 1, 2, and 1, negative 1, 3. And we're going to do negative 3 plus 2i minus 3 minus 2j plus negative 1, minus negative 1, so plus 1 times k. And so there we get the vector negative 1, negative 1, 0. And so our derivative, our final answer here, is the sum of these two. So our sum, the derivative of u of t cross v of t at t equals 0 is the sum of those two things. So we're going to get 2 plus negative 1, negative 2 plus negative 1, and 4 plus 0. So we get the vector 1, negative 3, 4. All right, we have the tools to find the vector, the tangent vector to a vector valued function at a point, but here we actually want to find the line tangent to our vector valued function at a given point. So that line is going to be parallel to the tangent vector and passing through the function evaluated at that point. So here we have a function, r of t is 1 plus 2 sine t, 4 minus cosine t, and t squared, and we want to find the equation of the line tangent to this curve at t equals pi. All right, so we're going to choose an orientation for the line that is the same as the direction of r prime of t naught. So we need a couple of things. First thing we need to know is what is r of prime, or r of pi, because that's going to give us the vector at which we're making our line. And so that is going to be 1 plus 2 times the sine of pi, 4 minus the cosine of pi, and pi squared. Well, the sine of pi is 0, so we get 1. The cosine of pi is negative 1, so we get 5. And then we have 1, 5, pi squared. The other thing we need to know is what is r prime of pi. So first let's figure out r prime of t. Taking derivatives component-wise, we're going to get twice cosine of t, the sine of t, because the derivative of cosine is negative sine, so we have two negatives, and then 2t. So r prime of, not 0, pi, r prime of pi is 2 cosine of pi, sine of pi, 2 pi, which is going to be, the cosine of pi is negative 1, so we get negative 2, 0, 2 pi. So this is going to serve as our direction vector. So our tangent line, the tangent line that we want, we'll call it, I don't know, we'll call it m of t. I don't know why I'm using m, but whatever, m of t, that's our tangent line. That is going to be our point, or our starting vector, plus our parameter times our direction vector. And so we end up with 1 minus 2t, 5, and pi squared minus 2 pi times t. I don't know why I wrote that last one as negative. That should be a plus. So recapping what we've seen here, we know that we can find the derivative of a vector value function component-wise. Because the derivative of a vector value function is also a vector, it's going to describe both motion and direction, and tangent vectors then arise naturally. Tangent vectors are going to indicate the direction in which motion is occurring at a particular point on a curve. And we'll see shortly that these provide the foundations we're going to need to look at velocity and acceleration in three-dimensional spaces.